Hello. In this video we're going to be looking at Learning Objective 3 on Chapter 17, Lecture 15. So we're going to be looking at the pH of a buffer after a small amount of acid or base being added to it, or determining the correct concentration of weak acid and weak base necessary to make a buffer at a specific pH. So moving right into determining the pH after we've added a small amount of strong acid or strong base into a buffer. So with this, anytime we have a small amount of strong acid or strong base added into anything where we have a weak acid or a weak base, we're going to do what's called a partial neutralization. So we're going to use a BCA table. So we're going to take the amounts we have and figure out how many moles of each of our substances we have, then do a BCA table. We, in this particular example, are adding in sodium hydroxide. That's a strong base. As such, it's going to react with the acid portion of our buffer. So we're going to do the BCA table with the reaction of our weak acid with our base to produce our conjugate. And then with those concentrations, we can put it into our Henderson-Hasselbalch. So let's first convert into moles. So we have 0.500 molar acetic acid, and we have a buffer solution of 0.0500 liters, so we get 0.0250 moles of our acetic acid, and we have 0.250 molar sodium acetate. We still have that same volume for our buffer solution, giving us 0.0125 moles of our sodium acetate. And then lastly, we have the sodium hydroxide we're adding in. We have 0.100 molar sodium hydroxide. And we add in a volume of 0.0200 liters, giving us 0.00200 moles of NaOH. As I said, since we're adding in strong base, our BCA table is going to be used with the acid on the reactant side. It will react with our base hydroxide to produce, well, actually sodium. It's going to react with our sodium hydroxide to fully react and produce sodium acetate and water. Okay, we're now going to, into here, put our moles that we started out with prior to the reaction. So we started out with 0.025 moles of acetic acid, 0.00200 moles of sodium hydroxide, and 0.0125 moles of our sodium acetate. Our sodium hydroxide is our limiting reagent, so we'll subtract that from both of our reactants and add to our products. And after that neutralization, we have 0.0230 moles of our acetic acid, 0 moles of sodium hydroxide as that fully reacted, and 0.0145 moles of our sodium acetate. Those can then either be put directly in because our volume will not change, or if you'd like, we can also go through and solve for volume or solve for concentration. So if we solve for concentration, we get 0.329 molar sodium or acetic acid, and then we get 0.207 molar sodium acetate. We can then put this into our pH is equal to pKa plus log base over acid, our Henderson-Hasselbalch, our Ka of acetic acid of 1.8 times 10 to the negative 5, so our pKa for that would be equal to 4.74. So I'd say, okay, pH is equal to our pKa, 4.74, plus log base concentration, 0.207, divided by acid concentration, 0.329, giving us 4.54 as our pH. Now, as a note, I said we could also just put our mole amounts in because they're in the same volume, so I just want to show that real quick. So if we do just moles, we do pH is equal to 4.74 plus log 0.0145 moles divided by 0.0230 moles. The moles will cancel out, and when we do that math, 4.74 plus log 0.0145 divided by 0.0230, we get 4.54. So either way will work, either concentration or moles, as long as you have them both in the same volume. Okay, let's look at what's called the buffering range. So the range that a buffer is working. So it is the pH range for a buffer solution. So the range where it's still considered a buffer. Okay, so our range, or pH range, or buffer range, is going to be plus or minus 1 from the pKa. Anything above or below that, we do not have the correct ratio of acid to base to be considered a buffer. So if we want to increase, or we want to maximize our buffer range, the best way to do that is to give equal volumes of acid and base, or use equal molar amounts. When we use equal molar amounts of acid and base, we can increase our buffering range because pH will then be equal to pKa, so we can go for a whole pH unit before our buffer becomes no longer usable. Okay, so as a note, we can figure out when a buffer is no longer a buffer, or when is a solution no longer a buffer. And that is when we have a ratio of acid to base that is outside of the range of 0.1 to 10. So if we are less than, if we are less than 0.1, or greater than 10. We are no longer in the correct acid to base ratio to be considered a buffer. And then if we see a pH change greater than plus or minus 1 from the pKa. We can also look at what's called the buffering capacity, or buffer capacity. So it is the amount of acid or base that a buffer solution can neutralize before it is out of our buffering range. Okay, so generally, we don't actually do anything to calculate the buffer capacity, but what we can do is increase our buffering capacity. And we do this by increasing the concentration of our conjugate acid-base pair. So the greater the concentration of your acid and base in your buffer, the greater your buffering capacity. Okay, so if we have a aqueous solution, we want to look at or evaluate what we are starting out with and determine what we need to do. If we have just an acid or base, we cannot use our Henderson-Hasselbalch, okay? Because this is not considered a buffer. It's a common thing. Once people learn about buffers, they're like, oh, I want to use it for everything. But you can only use your Henderson-Hasselbalch if you have a buffer solution, so a weak acid in its conjugate base or a weak base in its conjugate acid. If you only have a weak acid or a weak base, or a strong acid or a strong base, you need to use your normal means of determining hydronium and hydroxide concentration. Which will either be stoichiometry if we have a weak acid or weak base, or a Rice table for weak acid, weak base. So with a strong acid, strong base, we're just going to use stoichiometry. So it will completely dissociate to produce hydronium hydroxide. And if we do not have a conjugate acid-base pair, then we need to use a BCA table first, and then a Rice table or Henderson-Hasselbalch. H.H. Henderson-Hasselbalch. So if we have a non-conjugate acid-base pair, then we need to figure out what we have by doing a BCA table, and then if we have weak acid or weak base left over, we can use Rice table, or if we do not have a weak acid or weak base, or if we have a weak acid and weak base that are buffers, form a buffer, then we can use our Henderson-Hasselbalch. If we have a conjugate acid-base pair, then we use a Henderson-Hasselbalch. This is a buffer, use Henderson-Hasselbalch. So, just as a note, you're going to see a couple ways of working with aqueous solutions. Sometimes you'll just have one acid or base, and you'll just use normal means. Sometimes you'll be given an acid and a base together. You need to figure out what, after they react, you have left over, and then if you have weak acid left over, you can use Rice table. If you have normal or strong or weak, strong acid or base, you're going to use normal means. Or if you have a buffer, then you can use Henderson-Hasselbalch. If you are given just a conjugate acid-base pair, then at that point you can use Henderson-Hasselbalch. But unless you're just given a conjugate acid-base pair, you're going to have to do something else before you can use your Henderson-Hasselbalch. Okay, let's try out a problem. So we want to determine the concentration of benzoic acid necessary to make a buffer with a pH of 4.5 if you have 0.500 molar sodium acetate. Okay, so we're given our concentration of sodium acetate. We want to determine our concentration of our acid given our Ka value and our pH. So first, go ahead and solve for your pKa. We have a pKa of 4.20. Okay, so we want a pH of 4.50. pKa is 4.20, and we want to solve for log. Our base concentration is 0.500. Our acid concentration is what we want to solve for. Okay, so subtract 4.20 from 4.5, we get 0.30 is equal to log 0.500 divided by our acid concentration. And we solve for this. We take both sides to the 10. And then when we do some math, we get an acid concentration of 0.250 molar. So we basically want a 1 to 2 concentration of acid to base. Okay, that's it for this video. I will see you guys for lecture number 16.